Welcome back to the classroom. My name is Mr. Wong. So last lesson we actually talked about Earth's gravitational fields. Um, we also talked about gravitational potential, total energy, and kinetic energy of planets and satellites going in orbit. So in this lesson, we're going to actually go through the same lesson, but we're going to be focusing on those questions. So just before we go into the questions for gravitational potential, let's just quickly summarize what it is. We said that gravitational potential is the amount of energy an object has due to its position within the gravitational field of a larger object. So if we have a small object attracted by the gravitational fields of a larger object, then this is the formula to express it. The negative represents work being done with gravity to drag our object from a point of zero all the way to where they are positioned with the larger object. As we get closer to the larger object, our gravitational potential will decrease over time. And that kind of makes sense because obviously we're going further and further away from those gravitational fields. Okay, so there's that. Let's look at some multiple choice questions. Question 2 of this, it says the gravitational potential energy of an object near Earth's surface is changed. How could we do this? Applying a horizontal net force, applying the object to fall down 5 meters, holding the object stationary in the air, or ensuring the net force on the object remains zero. You can have a quick decision on that one. And we'll go to question 3 as well. A satellite orbits the moon with an orbital radius of 10,000 kilometers. Compare the same satellite with an identical orbital radius orbiting Earth. The satellite orbiting the moon would be moving faster, have the same centripetal force, have greater kinetic energy, have a longer orbital period. So pause this video here if you would like to work out those two questions. I'll go through the answers in 5 seconds. Okay, so for question 2, the answer is B. And to kind of demonstrate why that's the case, the formula for gravitational potential is simply GMMR negative. So if we change the object's position towards the Earth, we will change gravitational potential. Our next one is the orbital radius. So this actually looks into orbital velocity, and you could use the Kepler's law, or you could use orbital velocity. Mind you, with orbital velocity, obviously you don't have things like the orbital period, which is the correct answer we have here, longer orbital period. However, what we can see is if the moon has a lower mass than Earth, so the mass of Earth is bigger than the mass of the moon, then the orbital velocity on the moon is less than the orbital velocity on Earth, which leads to a lower or larger orbital period. So 2 pi r over t. So if this is large, that means that was small. Okay? And so I'll change that around because for our moon, this was small. That means this was large. Okay, cool. All right, so question 4 and 5. Asteroid has an altitude of that value there above the ocean. What is the gravitational potential? We have a newly discovered planet that has a mass and radius that is double that of Earth. What is the acceleration due to gravity? I'll give you 5 seconds to have to think about how to approach these two questions. You can pause it here if you would like to take your time to work it out as well. Okay, so the answer for 4 is C. And the way you do that is simply do your substitutions. 6.67 10 to the power of 11 times the mass of the asteroid, mass of Earth from the looks of things. So that's on your data sheet if you need the relevant values. And then over R, which would be the radius of Earth plus the altitude we're dealing with. Okay, and that gives us that value there. Question 5, a newly discovered planet. So we are looking at G equals to M GM over R. Okay, gravitational acceleration. So if we are looking at these values, one is, let's see, it has double the mass and the radius. So both a mass and radius that is double that of, that should be squared, sorry. So it would be G2M over 2R squared. Go that, we go 2GM over 4R squared. So we would actually find that the gravitational acceleration would be half the amount of Earth. So it'd be 4.9. Okay. This one is on potential energy and orbital speed. This is actually from the 2014 paper, question 6. A satellite is in a high orbit around Earth. A particle of dust is in the same orbit. Which row of the table correctly compares their gravitational potential and their orbital speed? Okay, so if we have a look, gravitational potential, obviously you pause the video here if you would like to have a go, but if not, I'll be explaining the answer here. Okay, so gravitational potential, the formula is like so. So big M is the mass of the Earth, little m is the mass of the satellite or the mass of the dust. So if a satellite and dust are going to be of different mass, that means they have to be different in potential energy. So A or B would be correct in this case, but we haven't looked at orbital speed. Orbital speed, when we did the derivations, was this value here, right? Square root of gm over r. So we know that the only thing that affects orbital speed is the distance they are from the planet. In this case, they have the same orbit, so the same distance, and also from which object they're orbiting around. Now, they're both orbiting around Earth, which means they would both have the same orbital speed, so the answer would be A. Okay, the graph shows how the gravitational potential energy of a satellite changes with its altitude. What is the change in gravitational potential energy of the satellite when its altitude is reduced from 14,000 to 400,000? So we go from about this position here to about this position here. Okay, around there. So you do your interpretation, you should find that the answer is negative 2.8, 10 to the power of 9 joules. Okay. So let's have a look at some other questions. Okay, so question 8 here is asking us to calculate the gravitational potential of our particular satellite. So negative g, m, and r. So it's negative 6.67 10 to the power of 11 times the mass of the Earth times the mass of the satellite over the radius of the Earth's orbit, which in this case is given as 6.38 10 to the power of 6, plus the altitude of orbit. Oops, one too many zeros. So we have that. And we get a value of approximately negative 7.55 10 to the power of 9 joules. Okay, so there's that one done. Number 9, it says, what's the change in potential energy of a satellite with a mass of 75 kg when it's near Earth orbit with initial altitude is that, and then when it decays into this value here. So without showing the overall structure, let's just look at the final value. So 6.67 10 to the power of minus 11 times the mass, so mass of Earth, times the, what do we have, mass of the mass object? We have the orbit of Earth plus an altitude that goes down to 290 kilometers, convert that into meters, subtract that by essentially the same values we're dealing with here. But obviously by the initial change in the altitude. Okay, let's go through what the answer for that one is. And you record our answer down here. Okay, which is negative 6.7 megajoules. So one thing I did forget to add here is there was a subtraction. There's also a second of subtraction. That's a subtraction of potential energy, and then you have the subtraction of the difference. Okay, and now that we've gone through the questions for gravitational potential, we can also look at the questions for total energy of objects in a particular orbit. So we demonstrated a very clear relationship in our previous video of this relationship here, that the total energy of an object in orbit, obviously like as a satellite or as a planet in orbit, their total energy is equal to half the amount of the gravitational potential, and it's also the negative opposite or the opposite signage of kinetic energy. So kinetic energy is positive, total energy will be negative, and gravitational potential will be twice the amount of our total energy as we see here. We went through deriving the formulas for total energy. Just get rid of the ink marks. So we got that relationship, and then we saw this one here. We also mentioned how these formulas aren't given to you on the data sheet, so you do need to try and work it out yourself, or at the very least know how to derive it yourself. Okay, so let's go through doing some of those questions for total energy and kinetic energy. So the first thing is calculate the total mechanical energy of this particular satellite. Do hope I have enough space. Doubt I would have enough space, but so it shall be. So energy is then, total energy is added with gravitational potential, which I can't add the formula onto it. So we'll just do that. So it's negative, well, actually, the formula for total energy is GMM over 2R negative. So we just substitute that value in. And that gives us a total energy value of about negative 4.11 10 to the power of 11 joules. The next question is to calculate the speed of the satellite or its orbital velocity, which you can simply do using this formula here, or you can derive it out yourself if you don't know how to do it. And so if we have g as 6.67, really out of space here, but let's see if we can write it somehow. Mass of the Earth. No. Okay, so what we'll do, just give ourselves a little bit more space. So this is the formula we're using, gm/r. We know that the constant is this value here, 24. That's the mass of the satellite, or not mass of satellite, mass of the Earth, and then the radius distance between the two objects. Obviously, if you're doing an actual exam, try and do it a little bit more neater than what I've done here. And we get a approximate orbital radius or orbital speed of 10,690 meters. Okay, that's done there. Okay, next one is question 11. It says find the potential, kinetic, and total energy of the orbit around the sun. So as I was kind of running out of space, I will just show it to you on this slide here. So let's firstly find the value for the gravitational potential. And those are our substitutions. We substituted G, the constant, m/r, as you can see our values here. Don't forget to convert the 150 million first. So million has 6 zeros in it, and then obviously convert the kilometers into meters. You could just do 150 times 10 to the power of 9. That works too. That gives you approximate value of negative 5.31 times 10 to the power of 33 joules. Next, we know that kinetic energy is half the amount of gravitational potential, and it's in the opposite signage. You could use the formula for kinetic energy as well to calculate this, but if we remember this, let's just do this. And so that's the value of kinetic energy. Okay, 2.66 times 10 to the power of 33. We could also do the same formula for total energy because it's half the amount of the potential, or we can just write the kinetic energy value here and give it a negative sign. So that's kind of how you look at it there in terms of the total energy changes that we have with a planet or a satellite orbiting a larger object. Okay, and that concludes the calculation part of this lesson. Thank you so much for joining me up till this point. If you did find it useful, please like and subscribe if you haven't done so already, and I will see you next time.